Hello again, and welcome once more to a video introduction and illustration of IBM's WebSphere Application Server for z/OS, Optimized Local Adapters, or WOLA for short. This is the outline for the subjects covered in this 5-part series on WOLA. In this section, we'll cover the Java-side coding considerations for using WOLA. We'll start with a higher-level picture of the support to provide a framework for the details that will follow. The first point is that regardless of inbound or outbound, there is a lower-level set of code that supports the WOLA calls in WebSphere Application Server for z/OS. This consists of Java and native modules relatively low in the WAS architecture model. This support is enabled when WOLA itself is enabled for the cell. As mentioned, the process for doing that is well documented in the Info Center and the WP101490 tech doc, so we won't cover the details here. It is enough to say that the process is fairly easy and can be done in just a few minutes. For outbound support, IBM supplies a JCA resource adapter that implements the Common Client Interface. This resource adapter is called WOLA.rar and is installed into WAS in the same manner as other resource archives are installed, such as the CICS Transaction Gateway Adapter. You may use either a servlet or an EJB to access the Common Client Interface methods implemented in the resource adapter. For inbound support, the picture changes a bit. The first thing to note is that for WOLA calls inbound to WAS, the target must be a stateless EJB session bean. Further, the stateless session bean must implement a method called execute, and that method must be defined to accept a byte array in and return a byte array back. IBM provides a set of development class libraries for use when coding this EJB. The class library file is called ola_apis.jar and is supplied in the file system of WAS z/OS itself. The key is that the home and remote interfaces must be implemented using the WOLA class files shown on the chart. That's the essential framework of the Java-side coding considerations. Let's dig deeper. Now we'll take a closer look at the outbound support using the supplied resource adapter and its implementation of the Common Client Interface. The Common Client Interface is an open standard for data system access in the Java Enterprise Edition or Java EE environment. The two methods we'll focus on initially are the connection spec and interaction spec. We start with a WAS z/OS server and an external address space of a type we have discussed before. For example, batch CICS or IMS. The OLA.rar resource adapter is installed into the WAS node. This is done in the same manner as any resource adapter is installed. The resource adapter implements the Common Client Interface as defined by the Open Standards community. Further, a connection factory is defined and it carries a JNDI name of your choosing. The default is EIS/OLA, so we'll use that in our example here. Either a servlet or EJB is used to access the Common Client Interface and get access to outbound WOLA. As we stated earlier, before anything can happen, a registration must be in place. And as we stated earlier, the external address space always initiates the registration into the WAS server. The registration carries a name. If you recall our discussion of the BBO-A1 Reg API, one of the parameters was a registration name. The value supplied for that parameter plays a key role on the Java side when it calls outbound. Registration may be performed in a variety of ways. One way is to use the BBO-A1 Reg API. The other two ways are using the BBOC control transaction supplied in the WOLA support for CICS, either BBOC register or BBOC start server. When the registration is complete, then the Java-side program may begin the communication. The Java-side program beginning the conversation is the very definition of the outbound concept. The Java program then performs a Java::comp lookup of the connection factory you defined to the WOLA resource adapter. Then, the Java program invokes the connection spec impl method and passes in as a parameter the registration name to use to communicate to the external address space. For outbound calls, the native program in the external address space must host a service. In the section on the native APIs, we spent some time discussing the idea of the external program putting itself in a listen state and reacting when the call comes through. When the external program hosts a service, that service carries with it a service name. That's one of the parameters used on the BBO A1 Serve API, and, as we'll see, when the CICS link server task is used, the service name is really the CICS program you wish the link server task to invoke with a DPL. There are several different ways to host a service in the external address space. With the basic BBO A1 Serve API, service name is one of the parameters on that API. With the BBO A1 Receive Connection Any or BBO A1 Receive Connection Specific Primitive APIs, both have service name as an input parameter. The CICS link server task hosts a service, but it acts as a kind of proxy for the real service, which is your CICS program. For IMS, it is possible to call using OTMA. Rather than go into the details of that here, we'll simply refer you to the CDAT_OLA CF Consid article in the Info Center. Let's now turn to inbound calls. We start with our picture of the WAS server and the external address space, and we add to that the lower-level WOLA support in WAS we mentioned earlier. We bring in the stateless session bean, and we note the following key attributes of that session bean. The home and remote interfaces are implemented with the supplied WOLA classes as shown. The session bean implements a method called execute, which takes as input a byte array and returns a byte array. When the EJB is deployed, it is assigned a JNDI name. The external address space program initiates a registration into the WAS server. The registration is given a name. Registration is accomplished with the BBO A1 Reg API or the CICS BBOC register command or the BBOC start server command. The native program invokes the target EJB using either the basic BBO A1 invoke API or the BBO A1 send request primitive. In either case, the API requires as an input parameter a register name. This is what tells WOLA which registration to communicate over. Another input parameter is service name, which in the case of inbound calls is the JNDI name of the deployed target stateless session bean. When the call comes in over WOLA, the lower level function performs a Java::comp lookup of the named EJB. Then it does an IIOP call of the EJB. The EJB is then invoked and the byte array message is passed in. We mentioned that WOLA is in essence a low-level byte array pipe, and we mentioned earlier that while WOLA itself doesn't get involved in data layout issues, the higher-level applications do need to understand the data layout. On this chart, we're going to look at how to use the IBM Rational Application Developer Data Layout Wizards to create Java helper classes to handle data layout. Imagine you have a native program in an external address space, such as Batch, CICS, or IMS. IBM's Rational Application Developer, or RAD for short, provides a data binding wizard that takes as input COBOL copybook. The output from the data binding wizard is a set of getter and setter methods that define the layout of the data based on the copybook used with the wizard. WOLA remains a byte array pipe, but the higher level application code now understands the layout of that byte array. Those getter and setter classes and the other class files are packaged into the deployable EAR file. The chief designer and developer for WOLA is a gentleman named Jim Mulvey from IBM Poughkeepsie. He has produced a series of YouTube videos that illustrate the use of the data binding wizards to create the getter and setter classes. In YouTube, search on the string WASOLA1. That will yield 4 videos as shown on the chart. In these videos, Jim walks you through the use of RAD to create the data binding classes. We've established that an inbound WOLA call requires a stateless session bean that implements the WOLA classes for its home and remote interfaces. That works perfectly well for new EJBs you write for this purpose. But what about existing EJBs you don't wish to modify? Or ISV EJBs you do not have the ability or authority to modify? The answer here is much like we described in CICS. a WOLA bridge program that shields existing programs from knowledge or awareness of WOLA. The first part of this chart shows the same low-level WOLA support we spoke of earlier, with a stateless session bean implementing the WOLA classes as we just discussed. Picture in your mind the WOLA EJB then invoking other EJBs using standard EJB invocation mechanisms. This is done without any modification to the non-WOLA target EJBs. The WOLA bridge EJB would contain a client stub based on the interface of the target EJB. For performance reasons, there's a hierarchy of preferred location for those EJBs called by this bridge program. The best performer would be to have the EJB in the same WAS server as the WOLA bridge EJB. The next best approach would be the non-WOLA EJB in a different server, but in the same ZOS logical partition. The reason for that is because the ZOS TCP stack is intelligent enough to understand when a call is within the same LPAR. It then fast paths the call, cutting out the entire IP layer and performing what is known as fast local sockets to reach the target. Beyond that is the scenario where the call would be cross-LPAR or off-platform. That would certainly work, but in doing so, you introduce the network latency issues associated with full-stack network calls that may have multiple hops involved. It may be very fast, but it will necessarily include at least some overhead per call. And in a very high volume environment, every little bit of overhead adds up as the multiplier effect takes over. We trust we have provided you with a useful overview of the WOLA function. Please remember two sources of additional information: the WAS ZOS Info Center, which is the official product documentation repository; the WP101490 TechDoc at ibm.com/support/techdocs, where the IBM Advanced Technical Skills Organization maintains its repository of technical information. The first point we stressed is that WOLA is a cross-memory exchange mechanism built on a function present in WebSphere Application Server for ZOS since the beginning, a function called localcom. It became available in the WAS ZOS 7004 level of maintenance. Its mission is to provide a very fast, very low overhead, very low latency pipe, and that's what it is. The external address spaces supported for this cross-memory transfer include batch programs, CICS, and IMS. The CICS support offers a very special function called the link server task, which shields your existing CICS programs from any knowledge of WOLA. Most of the benefits without having to recode your programs. For native programs, there's an API set, and that API set is supported for the programming languages shown on the chart. WOLA comes with a set of Java class libraries for program development and a resource adapter that implements the common client interface. Native language programs may use the APIs to gain access to the WOLA exchange mechanism. So, WOLA is a powerful, low-level memory-to-memory exchange mechanism. It achieves throughput by avoiding network overhead and object serialization overhead. It's not a universal solution to all things, but when the solution calls for it, it excels. Look for opportunities to use WOLA to solve your business requirements. We end with what sounds like a marketing tagline, but in truth exposes an underlying reality of WOLA. WOLA is all about exploiting the capabilities of the platform. The platform is ZOS. ZOS has cross-memory services between address spaces. WOLA simply makes that available to you for access to and from WAS on ZOS. On behalf of all those who have worked to make WOLA available to you, we sincerely thank you for the time you've invested in this video series. And we thank you for your continued trust and support in IBM for your business solutions.